Good morning, class. Hope you had a wonderful weekend. Today's lesson is going to be about electrical resistance and Ohm's law. So I have if you've noticed the diagram on the right here, it's a picture of, if any of you are Star Wars fans, it's a picture of Supreme Leader of the Resistance. I believe Snoke is his name, I think. And I recorded this video lesson on, or made this PowerPoint on the Star Wars Day, which was, I think, last Monday. So anyways, I thought that would be something to include the whole Star Wars Day in the lesson. So moving on, we're going to talk about what resistance is. So electrical resistance is basically just a property of any substance that slows down the flow of electrons. Okay, so therefore slows the current down within an electrical circuit. For example, if we want to be specific, we're talking about electrical circuits still. Resistors are electrical devices used in circuits to impede the flow of electrons, so slow them down. The greater the resistance, the more the potential drops. That is, the potential difference gets bigger, and I'm going to explain this in another diagram in a second. So as more energy is required to push a current through the wire. So as you hopefully recall from the last lesson on potential difference, we discussed the fact that there is a huge difference in the amount of a potential energy that exists at both terminals of a cell or battery, and then again at the beginning and the ending of a load, because as the electrons leave the negative terminal of that cell or battery, they're fully charged, they have lots and lots of electrical potential energy, but as they go through the circuit, they go through those conducting wires, they go through the loads, they're losing the potential energy. And so anything that causes these electrons to lose that electrical potential energy are known as resistors, and loads are examples of resistors. So a light bulb, a motor, a fan, a heating device, a blow dryer, those are all examples of loads, but they're also resistors because they slow down the electrons. So the famous scientist George Simon Ohm, basically he lived between 1789 and 1854. He made this discovery of the relationship between potential difference and current, and he discovered a relationship while he did lots of experiments on studying the different wires and the resistance within these wires that varied in thickness and in length. And he was basically the first scientist to publish results of these experiments on the resistance of different or various sizes and lengths of wires. And that's why we call these, we simply call these devices resistors, because they basically just do that. They resist the flow of current. And this relationship between current and potential difference is known as Ohm's law. This is just a graphical representation of Ohm's law. So as you can see, that as the potential difference in volts increases and the current in amperes increases, there is a linear relationship here. So it's a direct relationship between the two, and basically it's the resistance also increases in ohms. Okay, so when you have any of these two variables, you can figure out the third variable. So for example, if you want to figure out the resistance of a material within a circuit with a resistance of a load, for example, and you know the potential difference, you know the voltage of that that's entering and exiting the load, and you know that the current that's passing through that load, you can figure out what the resistance is. And vice versa. You can find out how fast those electrons are moving through a particular part of the circuit or load if you know the potential difference and you know the resistance. So this relationship is between these variables is very important in for electrical engineers and figuring out how circuits work and how what types of materials to design certain technologies. So resistance, again, so conductors such as metals, different types of metals allow electrons to flow freely through them and therefore have low resistance values. Now, there's different types of metals, and some will allow for electrons to flow more freely than others, but in general, conductors allow for low resistance values. Whereas insulators, they basically, this is an insulator, this is a diagram, I know it's been cut off, but it just represents a material that is more insulating, and the electrons, they're not easily able to get through this material as readily as within a conducting material here on the top. Okay. Resistance is measured just like voltage and current, and a ohmmeter is what is the device that's used to measure the resistance of different types of resistors. So when a substance resists the flow of electrons, it basically what it's doing is just slowing that current and converting that electrical energy into a different type of energy. So when you have a light bulb, for example, when the electrons are entering that light bulb, which is the load, which is also considered a resistor, the high electrical potential energy is converted into light energy, and then there's also some wasted energy in the form of heat, but the resistor slows down the current so that it can convert that electrical energy that's coming in into a different useful form of energy. So the more resistance a substance has, the more energy gained by the substance. It's radiated to its surroundings as heat or light energy. Like in this diagram here, this is a oh God, I forgot what it's called now, but it's an element. Yes, an element of a stove, and people use this resistor for cooking. A resistor is any a material that can slow current flow. So in a light bulb, the filament's hot. This is a filament right here. You can barely see it, but it has high resistance. So it really slows down those electrons. And as it does, it uses the electrical energy and converts it into light energy. And that's how, because the filament is made up of a very special type of metal that can allow for that to happen to create light. So resistors can be used in addition for producing light, and those are loads. Light bulbs are an example of a load. That hot plate here, that element on a stove is an example of a load or resistor. But we can have resistors that are just made and placed within a circuit to control the flow of electrons, to control the current, and they're just there to do that job and no other job. So in a circuit, electrons have a higher potential difference as they enter a resistor compared to when they leave the resistor, because they use up some of that energy in passing through the resistor. So if you can see, like, these are just examples that I found. This one, if you look at the potential difference here, so from here to here, there's a potential difference of 12 volts. And as the electrons are moving around the circuit, when they leave that battery, they've got 12 volts. Lots of electrical potential energy as they go and they come through this first resistor. This is that resistor symbol. They lose all that potential energy, and from here to here across that load is again 0 volts. So they can be used, they can be put in place like so to reduce the flow of electrons on purpose. So imagine electrons entering a resistor, again, as being at the high end of this is a ramp, just an analogy, where they have lots of or high potential energy in the and as those electrons leave the resistor, leaving the resistor are at the bottom of the ramp, where the potential energy has basically been converted into another useful type of energy for a light bulb. These are different types of resistors here, the different that are used in different types of technology. And as you know, this is a resistor symbol. And on the left side here, this is another resistor symbol that you probably haven't seen before. It's not within your textbook, but this is an example of a resistor. And there's different variations of these symbols, because there's variable resistors as well. But we don't need to get into that much detail for the purpose of this course. So a wire wound resistor, these ones right here, they're basically made of a very special metal, heat resistant metal, and wrapped, this right over here, this is the metal, and it's wrapped around an insulating core. And the longer and thinner the wire, the higher the resistance. So they are available with values from 0.1 ohm up to all the way up to 200 kilo ohm. Carbon composition resistors, they're made up of a mixture of carbon and other materials. And the carbon mixture is molded into a cylinder right here, like so, with a wire at either end. And by varying the size and composition of, like you can see the variations in the diameters of these cylinders, they can produce the varying resistances. Okay, so from 10 ohm to 20 mega ohm. Molded carbon resistors are cheaper to make than wire bound resistors. For example, these are more expensive than these. We can use an analogy again to describe resistance within a wire. So if you are thinking about like this dam, water going through these two different types of pipes, so that you can see that there's a lot more water that is able to go through this wider pipe compared to this one, which is